Bienvenue à tous. Welcome everybody to this short conference about spectra and geometry of large objects. During 2 days, we will explore various notions of geometric and spectral convergence and see how they are intertwined. This morning, we will listen to 2 talks about the very general setting of metric measure spaces. We will also have some talks that are more focused on hyperbolic surfaces. So we will have, and also tomorrow we will see more probabilist aspect. So I think we will be able to compare very diverse point of views. Before we start with the talk of Nicola Gigli, I have an announcement. So I reserved a table for about 25 persons at a nearby restaurant. And yeah, there are still places left, so I will circulate a sheet, and you can choose what you would like to eat. And I need to tell the restaurants a little in advance, maybe around 11:30, what people have ordered. And I think that's all I wanted to say. So it's a pleasure for the first talk of the morning to welcome Nicola Gigli, who came from Trieste, and he will give a survey talk about various aspects of metric measure spaces from the point of view of the Giorgi and Gromov.
Thank you very much.
Maybe one last thing, if you want to ask questions, it's a bit better if you use the microphone. But I know it's sometimes difficult to circulate it, but I will try.
Maybe I can repeat the question if you don't reach
yes,
a microphone, so for recording purposes, that's certainly doable. Yeah, thank you very much for the invitation. Merci beaucoup pour l'invitation. I know it's a bit of a tradition, you mentioned it, Nalini, to give talks in French in here, but I'm afraid I cannot dare to do, so I'll be missing from France in more than 10 years, so I'll stick to English, and I apologize for that. Now, concerning the title of my talk, so first thing you might notice, you might think, I'm using 2 big names, I mean huge names in math, just to advertise, my own talk, and in fact, that's a little bit right, and even worse than that, I wrote a survey on the topics that I'm going to discuss today, with precisely the same name, so in case you find it anyhow interesting what I'm going to say, you can archive, you can find this survey. Now, I came here, in reaction to an invitation from Nalini. She asked me to maybe present some aspects about spectral convergence in relation to lower Ricci bounds. And I thought this was a good opportunity to mention that whenever we speak about convergence of either manifolds or non-smooth objects with a uniform lower Ricci bound, not only you have spectral convergence for the Laplacian, but in a very precise sense, you have convergence of the Laplacians in these varying spaces. And in order to make rigorous this statement, it is very useful to have in mind what it is gamma convergence, which is a notion introduced by Giorgi like 40 years ago or something, maybe even 50, about convergence of lower semicontinuous functions. Now, this statement is extremely obvious to people that are familiar with gamma convergence, and maybe they come from a calculus operation background, to the extent that if I make this claim to an audience, experienced in gamma convergence, they would say, that's obvious, why do you even make such a statement? That's sort of self-evident. But maybe it is a little bit less so for audiences which are not, accustomed to gamma convergence. So in a sense, the title really reflects the fact that the message that I want to convey is that whenever you have a sequence of metric measure spaces converging in the measure Gromov-Hausdorff convergence, that's what Gromov is, it's very natural to attach to this kind of sequence gamma convergence of suitable lower semi-continuous energy functionals on them. So in some sense, the talk is about the interaction between these 2 things. All right, so, and here is the plan. So we just, quickly introduce the topic, and then I will discuss this measure Gromov-Hausdorff convergence and this gamma convergence, and then I will go to stability statements. Not so many proofs in this talk, just a few of them. Take this more of a survey. So what is this talk about? Yeah, so stability results in connection with lower Ricci bounds. in whatever sense. A very, very quick and dirty introduction to what is measure Gromov convergence and what is gamma convergence. And a very, very quick and dirty introduction to the theory of RCD spaces. And I shall focus on so-called dimension-free theory. So when you speak about lower Ricci bounds, from the geometric perspective, they are typically, they are interesting when you couple a lower Ricci bound with an upper dimension bound. Now, for me, this upper dimension bound is going to be plus infinity, so that's why, dimension-free theory. I do so for, I guess, a few reasons. The first one is that the theory is simpler to explain. So if there's to be an introduction, that's a good starting point. And the second is that this workshop is about geometry of large objects. So I guess infinite dimensional objects, they can be quite large. What this is not about are other extremely interesting aspects of the theory of RCD spaces and Ricci limit spaces, such as rectifiability results, structural results. There is a beautiful theory, essentially due to Chaire and Kolding, apologies, back in the late 90s, beginning of the 2000s, where basically they take sequences of manifolds with uniform lower Ricci bound and uniform dimension upper bound, and they see how metric can degenerate along such a sequence. And they investigate, among other things, for instance, rectifiability properties of limit spaces. This is not what I'm going to do. From the geometric perspective, maybe that's the most interesting thing to do, but I shall not do this. In some sense, if you want to think about a PDE analog, for when you study PDEs, there is first, the existence theory and then the regularity theory. In this picture, you can think my talk as the existence theory, and then the regularity theory would be the structural results, a la Chaire and Kolding, that I will not discuss. Another thing that we shall not discuss are extended metric measure spaces. So for me, a metric space is an object where the distance is never plus infinity, which, okay, it's a pretty standard assumption, but for some applications, in particular for applications coming from probability theory, this may be a little bit restrictive. Think to the Wiener space and the Cameron-Martin distance that is very often plus infinity. That kind of object could fit into the theory of RCD spaces, and judging from the title of the talk of Koei Suzuki, I think he's going to mention some of this, but I won't. I will not really discuss latest development of theory. Frankly, I think that the most recent result that I will mention goes back to 10 years ago. And so I will don't expect a set of complete bibliographic references. There are more than 100 papers devoted to RCD spaces and their properties, and just a few things I will mention. All right. So two key nonlinear weak topologies. When I brought this survey, the Giorgi and Gromov working together, I tried to make a little bit of an exercise to try to find what I thought were the two commonalities between this measure Gromov-Hausdorff and this gamma convergence. And I think that thinking of them as the weak topologies in the relevant spaces could be helpful for at least somebody who is not familiar with these topics, in order to just put this concept in the greater picture of math. So I will say now a few completely real facts, okay? But but let me state them. So what is a weak topology? Okay, I don't know. Maybe we can discuss that a weak topology is a topology for which we have compactness. Perhaps after imposing some bounds on the size of the relevant objects, we do have compactness. Now, of course, it's very easy to build compact topology. Just pick a topology with very few open sets. The trivial topology, any set is compact. This is not very interesting because we typically, we as an analyst, I guess, we want to have unique limits, and unique limits are very much related to Hausdorff property. And in order to have the Hausdorff property, you want to have more open sets. And now imagine you have a chain of topologies on the same set, one including the other. Of course, the fewer open sets, the more compact sets you have, and the more open sets you have, the more separation property you have. Your dream, a good topology, for instance, could be a topology which is both compact and Hausdorff. That's, if that happens, we are very happy. And in thinking of this, it should be, it's important to keep in mind the one topological rigidity statement. It's a very basic result in topology that tells that if you happen to have a compact Hausdorff topology on a set, then any weaker topology is not Hausdorff, and any stronger topology is not compact. So you only have, if you have on a chain of topology, you have one which is both compact and Hausdorff, that's your topology. So if you happen to have, for instance, a set, and you have a compact Hausdorff topology which is somehow compatible with some of this construction on that set, well, that's there's a good chance you might call that topology, the weak topology, the correct weak topology on the set. By the way, this topological rigidity statement is often stated as a continuous bijection from a compact into an Hausdorff is an homeomorphism. That's totally equivalent to this topological rigidity statement. Now, if I state this way, one could say, well, then it's easy, to find the correct weak topology. Just look in any reasonable chain of topology, add compacts, add open sets if you don't have enough, and take them out if you have too many. But in fact, part of the job here is finding the underlying set on which you can actually find these compact objects, and typically this requires lowering the regularity of the objects involved. So what Gromov did to define his measure of Gromov-Hausdorff topology or convergence was basically to replace smooth manifolds, or to start from smooth manifold and go up to metric spaces or metric measure spaces, as is going to be in my talk. And what the Giorgi did was to start from smooth or maybe functions with convexity property and forget about them and just focus on the lower semicontinuity property. Of course, there is not a totally parallel theory you could build up starting from upper semicontinuous functions. The choice of lower semicontinuous functions just because the functional we tend to work with in calculus operation tend to be lower semicontinuous, but you can put a minus sign in front of every function inequality that you have, and you would get a totally symmetric theory. All right, so what is measure of Gromov-Hausdorff convergence? In fact, I could define a measure of Gromov-Hausdorff distance and then speak about the convergence as the topology induced by this distance, but I shall stick just to what is a converging sequence. And just for simplicity, let me focus on the case of metric measure spaces where the total mass is 1. So the reference measure is the probability measure. This, of course, takes out a lot of interesting spaces, like RD, for instance. But the generalization to non-finite measures in this setting is somehow not that complicated. I want to say not trivial, but not that complicated from the application that I have in mind. So just for simplicity of expression, we focus to this. So a metric space, all metric spaces for me are going to be complete and separable, and then is going to be a probability measure, Borel probability measure on it. And if you have such a sequence of spaces, I say that they converge to a limit space provided we can find, in a measure of Gromov-Hausdorff sense, provided we can find one big complete metric space Y, and isometric embedding of all my spaces into Y, in such a way that once I push forward my original measures, Mn, in Y through these embeddings, what I get are measures that are weakly converging. Okay, what does it mean, weakly converging? Well, in this setting, maybe I'm not locally compact, so better I don't use a continuous compactly supported function. I shall pick continuous boundedly supported function. And what I ask is that for any phi bounded and continuous on this huge metric space Y, if I do the integral phi composition In with respect to the n measure, this converges to the integral phi composition I infinity or iota infinity with respect to the limit measure. Okay, that's measure Gromov-Hausdorff convergence. There are a couple of things I should, well, at least one thing I should prove. I should prove that the limit is unique. That's an exercise. Okay, so I will not actually do that. But if you have the same sequence converges to two different metric measure spaces, maybe through two different embeddings onto metric space Y and metric space Z, then in fact you can prove that the two potentially limit metric measure spaces are isomorphic. Okay, isomorphy means that there is a measure preserving isomorphisms between the support of the measures. From the perspective of this definition, whatever is happening outside the support of the measure is totally irrelevant in some sense. We should think as, xdm is, for instance, always isomorphic to support of m, dm, okay? Now you can wonder, hold on 1 second, so this is just convergence of the measure, where it is convergence of the distances. Why I mean, what is going on over here? And in fact, convergence of the distance is implicit in this definition through the fact that the maps In are isometries. And in many particular cases, but interesting cases, for instance, when the dimension is uniformly bounded in an appropriate sense, for instance, when the measures are doubling, then automatically the distances converge to the limit distance in the so-called Gromov-Hausdorff sense, if you know what it is. If you don't, doesn't matter. You just stick to this definition, okay? Now, I mentioned weak topologies. So I mentioned that you should think this as a weak topology, weak convergence for metric measure spaces. And I mentioned the weak topology should come with a compactness statement. So what's the compactness statement here? And that is Gromov, of course. So Gromov's pre-compactness statement reads as follows. Take fixed three numbers. K is a real number, n is an integer, non-negative, and d is a non-negative real number. And consider any sequence of Riemannian manifolds with Ricci curvature uniformly bounded from below by k, dimension uniformly bounded from above by n, and diameter bounded from above by d. Okay? For me, Riemannian manifold is connected, complete, smooth, no boundary. Okay? Now, HMN can be seen as a metric space, of course. You induce the Riemannian distance, and I can plug a very natural probability measure on it. The manifold has bounded volume, is compact, so I can just normalize the volume measure, and so be it. Well, then the point is that if I pick this perspective, then up to subsequences, this sequence must have a limit, which of course now has no reason to be a smooth Riemannian manifold. Typically, it won't be, but still there's a limit. Okay? And the proof is it's extremely short, and the idea is to use Bishop-Gromov inequality, which, by the way, Gromov proved in some sense with this purpose in mind, at least from my understanding. And the point is that you can bound in such a manifold you can bound the volume of bolts of small radius, because the Bishop-Gromov inequality is telling you that the reference measure is uniformly doubling across the sequence. So you can bound the volume. So the volume of a ball of radius r bounds up to a constant, the volume of the ball of radius to r. And then you double, double, double. The diameter is bounded. So after doubling a few times, you will get the whole space, which has mass 1 by assumption. So this gives you a uniform bound from below on the mass of small balls. And once you have this, given that the total mass is 1, there is a maximum amount of small disjoint balls that you can fit into your manifold. Now pick a maximal set of such disjoint balls, double the radius. By construction, this should cover your whole manifold. And this, in some sense, allows you to build epsilon nets of your given manifolds of uniformly bounded size. So in some sense, these manifolds can be uniformly approximated by finite sets. And once you have finite metric spaces, they trivially, if you have a sequence of metric spaces, each with 100 points, it's clearly, that up to subsequences, they have to converge somewhere, meaning, the distances between any 2 points must go up to subsequent to some limit. So that's, in some sense, is the whole point of the proof. Okay? All right. So that's a measurable outer convergence. Now, here is gamma convergence. Let me throw the definition to you, and then I shall comment it. Suppose you have a metric space X, and you have a family of lower semicontinuous functionals that can take, that go from X to R, possibly plus or minus infinity. At this level, I don't care. I shall define two functionals, the gamma lim inf and the gamma lim sup. And then I shall declare the sequence to have a gamma limit, provide these to agree. Okay? Now, the gamma lim inf is made like this. You want to compute the gamma lim inf at a point X. Well, then you pick all the sequences Xn converging to X. You look at the lim inf of En of Xn, and you took the inf among all the possible sequences Xn converging to your point. That's the gamma lim inf. The gamma lim sup is basically the same, except that you replace lim sup with lim inf. Sorry, lim inf with lim sup. Okay? And of course, the gamma lim sup, for trivial reasons, is greater or equal than the gamma lim inf. And if they happen to coincide, we say that the functionals do gamma converge. Now, if you've never seen this maybe tells you maybe nothing. So let me restate the definition. So an energy functional E is the gamma limit of the ENs if two things are true. First of all, we should have a joint lower semicontinuity property. I guess you can hear me, right? I hope the microphone is working. Right? So you should have this kind of semi-continuous. Sorry, here there is, I forgot an Xn. Sorry, I bet. So we have, for any sequence Xn going to X, you pick the lim inf of En of Xn, and that should be greater or equal than X, than E of X. Okay? But also, in some sense, E of X should not be too small. So this puts a bound on above on how big Ex it is. But it cannot be too small because we should have a recovery sequence. So for any X, we should find at least one sequence Xn converging to X, such that the energy is greater or equal, in fact, it's going to be equal, to the lim sup of En of Xn. Okay, there is an N here that I didn't write. All right? So that's an equivalent definition of gamma convergence. Notice that, let me start with a couple of remarks. I mentioned at the beginning that these functions are defined over a metric space, but in fact, let's be a little bit flexible. As soon as I'm in a world where I know what xn to x means, I can define an associated notion of gamma convergence, okay? Maybe I should pay attention on, properties of these, converging sequences, whatever, but I will not for the purpose of this. So whatever reasonable notion of convergence you have, topological, whatever, that's the job to, you can attach a gamma convergence statement. And another thing that might be worth to notice is that sometimes, especially if your functionals En are defined, say, on some Banach space or Hilbert space or something like this, some infinite dimensional space, sometimes you have two topologies, maybe a weak topology and a strong topology, and you can speak about, the gamma convergence relative to the weak topology or the gamma convergence relative to the strong topology, okay? And if, you have gamma convergence with respect to both these topologies, and the gamma limit is the same, typically, we call that, we say that the sequence most co-converges. Okay, that's, when you have two topologies in place, that's in the jargon that is used in the field.
So gamma convergence is only defined for sequences. You don't have a...
So there is a topology. There is a topology, but it's simpler, I don't know, it's just simpler, okay? In fact, it's easy to describe. Let me give you in one slide the definition of the topology. But that's a good question. But given that I'm going to apply this to functionals defined on metric measure spaces that are converging in some sense, for the purpose of this talk, this is the only thing that I will care about. And in application, this often happens to be the case. In some sense, even for measurable motor convergence, it's a topology, it comes with a distance, but then 99% of the time you just care about what happens for a sequence that is converging. But that's a fair enough point. By the way, if you have any questions or curiosity, please. Do you have a concrete example of this convergence? Yes, of course I have. No. Actually, let me first make a few comments. Of course, but that's of course I will make some examples. So the first, so given that, again, I mentioned this business about weak topologies and compactness, first of all, I want to convince you that gamma convergence at least has some compactness property. And the point is that if you just play a little bit with the definition, there is nothing complicated, just maybe time-consuming in checking the various implications. But you can see, for instance, that the gamma lim inf and the gamma lim sup are characterized, or you can define them in this way. For the gamma lim inf, at a point x, you pick a small ball, you look at the lim inf of the functional n on this ball, and then you take the ball smaller and smaller, and what you get in the limit when r goes to 0 is the gamma lim inf. And if you rather replace the lim inf with the lim sup, you take the gamma lim sup. Why do I mention this? Because if you happen to have a sequence of functionals for which in every ball the lim inf and the lim sup of this inf do exist, then this sequence must gamma converge. And by a trivial diagonalization argument, from this you conclude that if you have any sequence of functionals over a separable metric space, for instance, this must have a subsequence gamma converging somewhere. So that's the compactness in gamma convergence that you could keep in mind. Now coming to Nalini's question, so a way to think of gamma convergence, perhaps the way you think about gamma convergence, is about convergence of minima. So here is a statement that, again, it's totally trivial to prove if you just take 2 minutes and read the definitions. So suppose you have a sequence En that is gamma converging to a functional E infinity. And suppose that, two things. Suppose that you have points xn that minimizes En. And suppose that xn is converging to some point x infinity. Well, then the limit point x infinity is a minimizer for the limit functional E infinity. Okay? Now, with these two things, let me make two relevant examples. The first example is the following. Suppose our space X is R, and our functionals are like this. So I have a sequence xn going to 0, and my functional En is identically 1, except at the point xn where it is 0, and then it becomes 1 once again. So it just, this point is being moved. And okay, so if you believe this compactness in gamma convergence, up to subsequences, this should gamma converge somewhere. And of course, for instance, the sequence does not converge anywhere in the uniform topology, for obvious reason. It converges pointwise to the functional identical equal to 1, again for trivial reasons. But the gamma limit is the functional which is 1 here, and 0 in the limit point of the Xn. So the minimum is converging to the minimum. And in fact, this works even if I declare here the function, rather than being 1, let's declare that here, the function here is identically plus infinity. So you have a sequence of functions whose effective domain, the domain of finiteness of En has maybe nothing to do with the domain of finiteness of the limit functions, but still you can have gamma convergence. And this is a conceptual remark that comes at end when speaking about gamma convergence in relation to measure Gromov convergence. Now, perhaps a more interesting example is what happens, if you have a compactness in a function space, you should ask yourself what happens to highly oscillating sequence of functions, because compactness should kill oscillation. No? So suppose you have sinus of nx. Okay, this is not okay. This is 0. So on 0, 1, or whatever on R, pick sinus of n times x. This is your function En. And ask yourself now again, if you trust compactness gamma convergence up to subsequence, this should have a gamma limit. And of course, if we are, say, in some LP spaces, whatever, the weak limit would be the functional, identically 0. We take sort of the average. What gamma convergence does is something different. The gamma limit of this sequence is the function identical equal to -1. Okay? If you believe in this statement, you see that these minima are in some sense accumulating, and they become denser and denser. So in the end, you should have something like this. The verification of this statement again is totally trivial. For instance, by the equivalency stated in the beginning of this slide or the previous definition, it's totally trivial. But it's conceptually important to realize that what is happening. And you could say, come on, this is breaking the symmetry. Why we are choosing the bottom half rather than the top half? Well, that has to do with the fact that we chose to work with lower semicontinuous function rather than upper semicontinuous function. We had the other choice. We will go in some sense upstairs. Okay. What else? Okay, here is another remark. Sorry, no, I wanted to answer Nalini's question. So suppose the topology of gamma convergence is typically defined in the following way. It is the weakest topology that makes the map F to inf over K of F lower semicontinuous for any K compact inside my metric space. And the map F to inf over U of F upper semicontinuous for every U open set inside the metric space. There is a topology generated by this property, and the topology is precisely the topology of gamma convergence. Okay, so here K is compact, and U inside X is open. Maybe you cannot read. Okay, K compact, U open. Okay. All right. Other questions so far? Okay, let me make another claim about gamma convergence. This in applications is maybe not that useful. For me, it will be completely useless, but again, it helped me clarifying the role of gamma convergence in the big picture of convergences. So here's the point. Suppose we restrict the attention to, say, non-negative lower semicontinuous function, just for the sake of. And let's define a kind of, Moreau-Yosida approximation of the function. So fix K, natural number, and define Q key of E as with this expression. Okay. It is total. The following two facts are totally trivial. First of all, regardless of who is E, this functional Q K of E is K Lipschitz, because if you froze Y and you look at this as a map in X, this is obviously K Lipschitz, and I'm taking the inf of a family of K Lipschitz map. This is going to be K Lipschitz for trivial reasons. And the other trivial fact, which is consequence of lower semicontinuity, and maybe the fact that E is bounded from below, is that if you let K go to plus infinity, qk of E increases to E. Not hard to check. Because in some sense, in making this inf, you don't want to go too far from x, otherwise you pay too much of this guy. So you want to be close to x, and this in some sense is what creates this convergence statement. Okay? Why am I mentioning this? Because you can prove that for non-negative lower semicontinuous functionals, gamma convergence is equivalent to convergence of local uniform convergence, meaning on compact sets, of qk of En to qk of infinity. Okay? Why am I mentioning this? Well, because if you have uniformly Lipschitz functions, then up to subsequences by Ascoli-Arzelai, you can expect that on compact subset they should converge somewhere. So the way you can think of this statement is a sequence weakly converges if and only if after regularization it strongly converges. That's a way of thinking at gamma converge. No? This qk operator is a regularized operator, kind of the convolution, if you want. There's no convolution, but kind of, and it plays this role. All right. Way over time. Okay. Let me just mention how the two things can be used together. So suppose you have a sequence of metric measure spaces converging in measure Gromov sense, and suppose that you have a realization of this convergence. So you let us fix this big space Y and the isometric embedding of all our initial guys into this Y. And well, now once we have fixed this, we have a natural way of speaking, for instance, of weakly converging sequence of measures defined on these different spaces. What does it mean that Un, which is a probability measure on Xn, is converging to mu infinity, which is a measure on the limit space? Well, let's just embed everything isometrically into Y through these maps In, and let's ask ourselves whether we have weak convergence. Once we have this, now it makes sense to say that a sequence of functionals defined on probability measures on Xn, gamma converges or gamma limit sup to a certain function on probability measures on the limit space. Just play the game. No? Xn for now Xn is mu n, and with this kind of convergence. Okay, similarly, we can speak about weak L2 convergence or strong L2 convergence for sequence of functions defined on a varying sequence of spaces. So what does it mean that Fn, which is an n-depending function on L2 of Xn, converges weakly to a limit function, weakly in L2 to a limit function in F infinity? Well, two things should be true at the same time. First of all, I should have a uniform bound on the L2 norm. And second, the measures Fn and Mn should weakly converge to the measure F infinity M infinity. Oh, sorry, that's a typo. F infinity M infinity. My apologies. After embedding everything into the limit space.
And
okay?
Fn Mn means Mn multiplied by Fn.
Yes. This is really a measure with sign a priori. But I assumed the measures to be probability, the Fn to be L2, so they are L1, so the mass is finite. Still, I'm saying a comfortable situation. And for instance, with this definition, you have the classical sequential compactness, weak compactness of L2 spaces is there. If you have any sequence of L2 functions with uniformly bounded L2 norm, up to subsequences, they must have a weak limit. And also, the L2 norm of the weak limit is less original than the limit of the approximating L2 norms, much like for a given fixed space. And when is it that we define strong L2 convergence? Well, whenever we have weak L2 convergence plus convergence of norms. That's if all the spaces are the same space, this of course reduces to classical notions, but this makes sense even for a variety for a sequence for a convergent sequence space. There are a few things that are not entirely trivial. For instance, it is a priori not trivial, but nevertheless true, that if Fn strongly converges to F infinity and Gn strongly converges to G infinity, then Fn plus Gn strongly converges to F infinity plus G infinity. That's because the L2 norm is not a linear quantity, so in principle does not really easily passes to the limit, but it does. So that's a statement, if you want, that makes this definition compatible with what we have in mind. And of course, you can say, hold on a second, all of this depends on the realization that you fixed at the beginning. If you choose a different realization, then you are defining different notions of convergence of measures and of functions and therefore different gamma convergence. Yes, but not so much. So that if you have two different realizations, well then basically I want to say that they are the same up to automorphism of the limit space. So the convergence is essentially unique. If you have two realizations, okay, that's maybe you just rotated your limit space before putting into the limit object. All right. By the way, I want to mention before I forget, I didn't write it, and I should have, that the first instance of coupling this gamma convergence result and measure Gaussian convergence goes back to a paper in 2003 by Qua and Shioya, where they were very much interested in spectral convergence properties under measure Gaussian convergence, very much in line with what I'm doing, what I'm mentioning today. Through means that have nothing to do with optimal transport, but this is what they cared about. All right. Now let me come to, please.
Where was the gamma convergence?
Gamma convergence is in the fact that thanks for the question. In the fact that I defined the notions of convergences for objects, in these different spaces. So now I can say, for example, suppose you have a function, a family of functionals defined on the probability measures of xn for every n, included an infinity. Now it makes sense to say that they gamma converge with respect to that notion of weak convergence, for instance. So it's hidden. So I agree, it's hidden. But it's that once you have a notion of convergence, even if this does not come from metric topology, I know what it means that xn converges to x infinity, then I know what it means that functionals defined over xn, the gamma converge to functional defined over x infinity. Even if, and that's, let me stress once again this fact, even if the domains are different. Maybe here, let me mention this. Suppose, imagine that your space Y, where you are embedding everything, is R2, for instance, just for the sake. And imagine that Xn is being embedded, this is X1, this is X2, X3, X4, etc., and this is X infinity. So there is no overlapping in some sense between the Xn. So whenever I have a functional, for instance, over Xn, I cannot evaluate on Xn plus 1 or on X infinity. Or maybe a function or a probability measures on Xn, I can evaluate this function or probability measure on X plus 1 or X. Still, nevertheless, as soon as I have, and I have, thanks to this big embedded space, a notion of what it means that points in here are converged to points in there, I can speak about gamma convergence. Okay? Please.
So, because in the definition of the weak convergence, it's Fn, what's the...
It's here, you mean, sorry, the typo. This means that Fn, sorry, and thank you for asking. So this means that Fn Mn weakly converges, I should have written, to F infinity M infinity. And this means that for every phi continuous with bounded support over this big space Y, if I do the integral of phi composition In times Fn dmn, this converges to what you could guess. Make sense? Other questions? All right. Let me actually go to after a quite long introduction to the topic of the talk. So vast distance. Well, this is I guess is a quite it's not part of typical undergraduate studies, but it's now a quite popular concept. Whenever you have a metric space, you have a natural way of attaching a distance to probability measures on this metric space. Distances depend on a Holder exponent p, and I will just care about p equal to. So we just define the distance W2, and the W2 distance is between two probability measures. It's just defined as the inf of that integral. So I take all the possible couplings between the measure, I integrate distance squared, and then I try to minimize this and take the square root. Okay. Exercise. This is actually a distance. The only thing that could happen is that you have two probability measures. But for any admissible transport plan, the cost is plus infinity, so the W2 distance ends up being plus infinity. Well, then what do? We restrict our attention to probability measures with so-called finite second moment. If this integral is finite for some point x bar in our metric space, then it's going to be finite for every point x bar. And you can check that if you have two measures mu and nu with finite second moment, this infimum of the cost is going to be finite. And then on this set, W2 is actually a distance. It's a bit like when you find, so if we decide that the L2 distance is an interesting distance, well, then 1 second after, we restrict it to functions which have finite L2 distance from a nice function that we like, for example, the zero function. Here we do the same, we restrict to measures which have finite distance from measures that we like, for example, the direct data, okay? And a fact that, can be proved is that if your original metric space had geodesics, so curves realizing, the length, well, then the Varseness distance, the Varseness space also has geodesics. I will not prove this. If you don't know, but believe me, okay? That's a fact. And I mention this because I want to mention this important result. This is due to Sturm-Voronezh, but it comes after works of Otto Villani and Cordeiro-Raskin, Mechanisch, Mukesh-Lager a few years earlier. That tells, now here this Ricci curvature appears, and it has the following. Take a real number k, and take a smooth Riemannian manifold, smooth, connected, complete, no boundary. Then the following are equivalent. Well, the Ricci curvature is uniformly bounded from below by k, which means that for every vector v, Ricci curvature in direction vv is greater or equal than k times gvv. G is the metric tensor. Or something where no derivatives at all appear is true. So you take the Boltzmann-Shannon entropy functional up to a sign, okay? So integral of rho log rho, basically. And you check whether this functional is k-convex on the Varseness space. So a Riemannian manifold as a metric space has geodesics. Therefore, if you believe me what I mentioned the previous slide, the Varseness space also has geodesics. And once you have a metric space with geodesics, you can make sense of a convex function on this metric space. It's just a function that, along geodesics is convex. K convex is just, let's think k equals 0 if that bothers you, okay? So non-negative Ricci curvature is equivalent to convexity of the entropy in the Varseness space. That's a fact. The proof of this statement is, to prove this, you basically need to know how Varseness geodesics are made. So you need to be, proficient in optimal transport in some sense in order to actually perform the computation. But, it's provable, okay? Now, once you have this statement, you can notice that, the first point requires you to have derivatives. You need to know what is the Ricci curvature and what is the metric tensor and how to, compare them. The second property requires no smooth structure. It's like saying, a function, you can have two definitions of convex function. One is Hessian negative, the other one is, the convexity inequality is in place. Of course, when you think about convex function, you have in mind Hessian non-negative, but given that the function can in principle be no smooth, the actual definition is, the convexity inequality. And that's kind of the same. So once we have this theorem, it is, quite natural, I want to say, but that's, what a lot of Milanese Sturm immediately after this theorem by Sturm and Voronezh came out, we can define what it means for a metric measure space to have Ricci curvature bounded from below by k, whenever the entropy functional is k-convex in the Varseness space. Okay, that's not unreasonable. If the metric measure space comes from a smooth Riemannian manifold, then it's totally equivalent to our definition. Okay, to our starting property. Then why should anybody do this? Well, because if you go to weak statements, you gain compactness. And so maybe if you're interested in studying, for instance, properties of limits of manifolds with uniform lower Ricci bound, you know that this CD k infinity condition, curvature dimension condition, is stable under weak convergence. Then you are sort of in business. Okay. By the way, so curvature dimension, the first number is the lower bound on the Ricci curvature. The second number is the upper bound on the dimension. I'm putting infinity, as I was mentioning at the beginning of the talk, because I'm not speaking about dimension upper bound. But there are variants of this, and there are important variants where you do CDKN for some finite number n. Okay. All right. Of course, so speaking about stability, let's go back to this example of convex functions. If you have a sequence of convex functions, and which is converging in some sense to a limit function, and you wonder whether the limit function is also convex, if your only definition of convexity is non-negative Hessian, well then, in some sense, you want to ask C2 convergence in order to be sure that the limit function is also convex. But if you know that the convexity is actual, convexity inequality, then pointwise convergence is enough. Okay? So if you want stable notions with respect to weak topology, you should go, to definitions where, no derivatives appear. Integrated definitions are, much more stable than differentiated one. So do we have a stability result, or do they have a stability results for CDK infinity? Well, yes, they do. In fact, so this statement they prove is essentially the following. If you have any sequence of metric measure spaces converging, in the measure Gromov sense, then the relative entropy functionals do gamma converge. Okay? Actually, they never state the theorem this way. They never mention gamma convergence at all. That's the way I'm phrasing the result, but that's what they proved. Okay? And then, I'm phrasing it this way because it's, better for development of the theory, which I guess I will not be actually be able to show you. So how do you prove such a result? Well, let me just mention that, this has nothing to do with the specific form of the Boltzmann-Shannon entropy. It has to do with just any convex function of the measure. So if you have a function, little convex and lower semicontinuous, then you have this easy to check duality formula where integral of u of rho you can write in this way. This is a restatement of the Fenchel-Legendre duality for convex functions. And you have that in mind. You can easily prove this statement, and if you believe in this identity, it is clear that if mu_n converges weakly to mu infinity and mn converges weakly to m infinity, then the right-hand side passes to the limit. So for fixed phi, the right-hand side is weakly continuous in both measures. Then sup of continuous things is lower semi-continuous. So that's in some sense the gamma lim inf. Property, and the gamma lim sup goes by approximation. You first reduce to the case where U has continuous density, and then basically use that density to define the mu_n. It's technically complicated, but maybe conceptually easy to believe that this is true. Okay, and as a corollary, and that's why they prove this result. The corollary is that CDK infinity is stable. Why CDK infinity is stable? Well, I should check that if I have a sequence of functionals, a sequence of spaces where the entropy is k-convex, the entropy is k-convex even in the limit space. How do I check this? Pick two measures in the limit space. Approximate them with the gamma lim sup, with measures which are converging weakly and for which the entropy, in some sense, are no bigger than the limit 1. On the approximated spaces, you have the geodesic along which you have k-convexity. And then when you pass to limit up to subsequences, this geodesic must go somewhere, and then you use the gamma lim inf property to know that at the limit, in some sense, the entropy falls down. So at the extreme of the geodesic, you have the gamma lim sup property. In the intermediate level, you have the gamma lim inf, and you are in business. And you can easily check that, basically convexity is a stable notion under gamma convergence, under a little bit of compactness, which is present here. So I will stop in a couple of slides, but let me just, maybe mention a couple of things. And I apologize for maybe I took too long for the introduction, but at least I gave maybe a clear introduction. So here is where the theory did go after, Lotz and Villani gave the definition. Of course, the first question is, okay, how far are these spaces from smooth Riemannian manifolds? So which kind of theorems that I know and love in the smooth Riemannian world can be extended to this non-smooth world, and how can I use them to actually gain a new result about the smooth category? And in fact, there is an issue here. A potential issue from this perspective, because Finsler manifolds, or if you want finite dimensional Banach spaces, they do satisfy the CD k infinity. In fact, the zero, strictly speaking, the zero infinity, or even the 0n condition. Okay, so they are included. Banach-like geometry are included in this CD business. But much like the geometry of Banach spaces can be way more complicated than the geometry of Hilbert spaces, things can only go worse if you start adding curvature and topology. So the geometry of Finsler manifolds can be radically different from the Riemannian manifold. And moreover, and most importantly, we know from the Chigre-Kolding theory that if you have a sequence of Riemannian manifolds with uniform lower Ricci bound, converging and upper dimension bound, converging to a limit smooth Finsler manifold. Let's suppose that the limit, generally is not smooth, but let's suppose it is smooth and this is Finsler. Then it must be Riemannian. So a genuinely Finsler geometry cannot occur as limit of Riemannian geometry with uniform lower Ricci bound. This statement is called the almost splitting theorem. So if you ever heard about almost splitting theorem, it is telling morally this. So it's telling that Pythagoras theorem holds on small scales over Ricci limit spaces. That's the way you can read this. Okay? So because of this, you know that physical geometries are different. They not occur as Ricci limit. Well, then maybe inside this collection of CD spaces maybe just a bit too big, and we should somehow refine this condition, keeping the stability, but in some sense, keeping out physical geometries. That's it's something you might want to do. Okay. And this, in fact, is what motivated me to start studying, heat flow on this business. And just let me, maybe let me conclude mentioning, can I take 5 more minutes, Nalini? Okay, so we just introduced a couple of things about heat flow. Maybe what I want to conclude with, I want to convince you that heat flow is stable under a converging sequence of CDK infinity spaces. And so if you arrive there, maybe then I will not discuss further, but maybe if the heat flow is stable, then spectral convergence or Laplacian convergence. You might believe me, I guess, in some way. And in order to define heat flow in this business, I need to define gradient flows in a metric setting. This is something that has been a theory that has been initiated by Giorgi. In fact, he really had in mind the convergence of variational schemes under gamma, stability results related to gamma convergence, so very much in line with what I'm saying. And here is a fact. If you have a curve in a metric space, which is absolutely continuous, that difference quotient, the limit exists for almost everything. And we call it metric speed. That's an old result by Ambrosio. Okay? It's not obvious, but it's true. Okay? Take it as a first, differentiability result, kind of 1D Rademacher result for metric value maps. Now, if you have a function over a metric space, let's consider the descending slope. So how fast you can decrease this function if you're sitting at a point x as that limb soup over there. You can say, why do I care about how much do I decrease? Why don't I put, say, absolute value and I consider some approximate ellipsis constant or whatever? Well, because in applications, if I replace the negative part with the absolute value, what I get is something which is identically plus infinity. It's not in some sense, it's not useful enough. So it's better to deal with this sort of things. Now, it's a result you can prove, it's not obvious, but you can prove that if you have a k-convex function and lower semicontinuous, I forgot to mention, you have a curve, gamma, well then this kind of inequality is in place. This is a metric version. Imagine, so if I have a smooth function and a smooth curve and I differentiate in time E at gamma t, of course what I get is the differential of E at gamma t in duality with gamma t prime, and by Young inequality this is less or equal than 1/2 gamma t prime squared plus 1/2 the norm of the differential squared in gamma t, right? So if I integrate this, I get this property, and what is true in metric space is that I can prove this property even if I cannot do the chain rule. No? So that's instant.
Here you're not using K-convexity.
I am, to be honest, I am. So I need some regularity. So thanks for the question. Even on R, for instance, if E makes a jump, I cannot hope to recover, the difference of the value of E at the beginning of a curve and at the end of a curve as, integral of the derivative. So in some sense, this is like saying, if this right-hand side, if this integrand is in L1, then the functional E must be absolutely continuous along the curve. That's the kind of regularity. And this kind of regularity in this metric setting can be a consequence, for instance, of K-convexity and lower semicontinuity. Thanks for the question. But I need some, I want to, to say that, to use the fundamental theorem of calculus somehow. So I need some regularity of the function involved. But if you have this inequality that is always in place, then you can ask, you can notice when is it that I have, say, equality over here, and I have equality over here if and actually let me put a minus because for gradient flows I want to decrease. I have equality over here if and only if, in some sense, gamma dot is precisely minus the gradient of E at gamma t, right? By Cauchy's identity, Cauchy-Schwarz inequality and then Young inequality. So I can encode the property of being a gradient flow in a purely metric way. That's an idea of the Giorgi, by asking that the other inequality is in place. Okay? And the Giorgi initiated a theory that has been somehow, taken over by, continued, instead of taken over, instead of continued, by myself and Ambrosio and Savary, where basically there is at least an existence result associated to this kind of notion if you ask for, say, convexity and a little bit of compactness. Absolutely not trivial, but this notion is not empty, okay? And now, what has this to do with heat flow and lower Ricci bound? This has to do because of a beautiful fundamental result of Jordan, Kinderer, and Otto, which is this extremely famous, that basically tells that if you live in, say, Riemannian manifold, okay, they did this on RD, but that's the proof for Riemannian manifold is really the same. If you live on RD, and you look at this concept of gradient flow, where the functional is the Boltzmann entropy functional, the distance is the Varsian distance, then the kind of evolution that this gradient flow property singles out is precisely the heat flow. You take, so this a priori seems to have nothing to do with the Laplacian. There was a joke that Brenier did years ago that says, goes like something like, suppose in an alien civilization, they define the heat flow in this way, well then the guy who proves that the heat flow is linear gets the Fields medal, because there is nothing linear about this. Nothing linear about this. You have the Boltzmann-Shannon, you have this Varsian distance, whatever, and then the Laplacian, the linear Laplacian operator pops out on Riemannian manifolds. Okay. All right. So so their theorem in this sense was a bit more formal than the way I'm stating it, but they initiated a whole theory about gradient flows in Masterson spaces. This motivated, for instance, Ambrosio Savary and myself into taking back this idea of the Giorgi and putting them in place. So let me conclude with just one stability result. The stability result is this. Now, suppose that you have a converging sequence of spaces, xn to x infinity, converging in the measure of Gromov sense. And suppose that they are all CDK infinity, okay? So the uniform lower Ricci bound. And suppose that you have a sequence of measures mu n in xn, and this sequence is weakly converging to a limit measure, okay? And what I know is that also the entropies are converging and that the limit entropy is finite. So I want to exclude, say, Dirac deltas from my analysis. I need to start from, well, absolutely continuous measures. Well, then take gradient flow trajectories of the n entropies that are starting from un. Well, then they must converge to the gradient flow trajectory in with respect to m infinity starting from mu infinity. Okay. So maybe let me mention this. So I forgot to mention one thing. So CDK infinity is about k convexity of entropy. Okay. There is a nice theory about gradient flows of k-convex functionals of metric spaces. Jordan, Kinderer, and Otto tells us that if you start from a smooth Riemannian manifold and you take the gradient flow of the entropy, then what you get is the heat flow. Okay? Well, now it's a little bit natural to pick these CDK infinity spaces of L'Hostoum and Villani and study the gradient flow of the entropy. They come with one property. The entropy is k-convex with respect to Wasserstein. And Jordan, Kinderer, and Otto tells that in the smooth world, if we take the gradient flow of the entropy with respect to Wasserstein's business, we get the heat flow. So nothing is more natural, I want to say, than studying the metric gradient flow of the entropy with respect to Larsen space in this CDK infinity setting. And in my first paper in the subject, I proved uniqueness, which a priori is not trivial, but also stability results. So this kind of heat flows, they do pass to the limit. Okay, and my time is.
So you said in the Riemannian case, it may seem like a miracle that the gradient flow is linear. In general, it's not linear.
It is. In general, it's not linear. For instance, in a Finsler manifold, it is not linear. In a Finsler manifold, in fact, this is, in some sense, the beginning of the theory of RCD spaces, because, in fact, statement, the Laplacian on a Finsler manifold is linear if and only if the Finsler manifold is Riemannian. Okay. So if you believe in this statement, then as a consequence is that the heat flow is linear if and only if the manifold is Riemannian. Now, if you have this stability result, you start, seeing a little bit the light at the end of the tunnel, because now, if you start from a sequence of spaces where the heat flow is linear, and you have this stability result, then you conclude that the heat flow is linear even in the limit space. So you are ruling out Finsler geometries. Okay. So this is where the theory is going. But I'm afraid I took a bit too much time to introduce gamma convergence. So I think I just stop here. But I'm happy to discuss this in the next hours or days. Thank you.